Come on in, everyone. I'm looking for my roll sheet now. Feel free to ask me any questions, folks, if you have any. I am in the process of taking a photograph of the attendance because I can't find my roll sheet right now. All that. There are no questions. We got still about 2 minutes, everybody. My friend came up from Florida and is fixing my office and all my floors and basically fixing everything I was unable to do. So I'm finally getting my desk set up. I've got my bookshelves up, they're painted, life is good. Feel like I'm rich. Back to this. Okay, now it's about time's up. So again, anybody have any questions? Hopefully you guys have practiced some Gauss's law stuff. So you're actually supposed to be able to start with the closed integral of E dot dA equals Q enclosed over epsilon naught and use that to derive, for instance, the electric field for a uniformly distributed charge, uniformly distributed throughout a sphere of radius r, or for a conducting sphere, both of which I've worked for you. You could also do it for a uniformly distributed charge throughout a cylinder. So you take an infinitely long cylinder, and now you imagine, just like the sphere, that some inner cylinder within the cylinder has a certain amount of charge too. So calculate the electric field inside the actual cylindrical charge distribution, as well as outside. So that's another one you do. And you should be able to for a flat infinite plane. So those are all things you should be able to do. Make sure you can do that. All right, I got another person in, so I'm gonna take a screenshot of the of the roll again. All right, I've done that. Now I've got that finished. And let's say I got all 6 of you in here, all 6 of you that are attending. So no one has any questions? All right, with that in mind, what I'm going to do now is basically sort of the same thing we did when we went to chapter 7. In Physics 241, remember from chapter 5, we did Newton's second law, as well as chapter 4, we did Newton's second law. And then again, I'm going on the assumption that you took Giancoli's book or you took me for Physics 241. Obviously, it's different if you didn't. Chapter 22 in principle should be due tomorrow, but I have planned to move it back till probably I might move it back till Friday, I think. So one of your students, one of your fellow students just asked, is chapter 22 supposed to be due tomorrow? Since I actually finished chapter 22 Thursday of last week, yeah, I thought that was fine. But I'm probably going to move it back at least 2 days. So instead of it being due tomorrow, the 26th at 11:59 p.m., I'll put it back at least till the 28th. Oh. So, and I don't want to pile too many things up on the actual 30th or 31st. So that's probably the date I'll move it to. So make sure you get that done. You should have most of it done by now. There's also going to be an online test that'll come up really soon. I'm probably planning on putting that up either today or tomorrow. So keep an eye on that. Our last test actually our last test covered chapters 19 and 20. That was the face-to-face test. So now we're ready to do 21 and 22, which includes Gauss's law. So that one's going to come up soon. But again, you guys are supposed to be able to apply Gauss's law to find the electric field around various charge distributions. The main thing is the charge distribution has to have that symmetry so that you can solve for the electric field within the integral. Okay, that's a little difficult. It is like I said, Gauss's law as opposed to Gauss's helpful hint that sometimes works. It's just Gauss's law, but doing that weird thing where you're solving for the electric field, that only works when there's spherical symmetry, infinitely long cylindrical symmetry, which in the physics world, infinitely long means the distance from the place that you're studying to the end has got to be at least 10 times larger than the distance from the place you're studying to the actual object. So if you're closer to it than 1/10 of the way away from the end, then that's usually a pretty good estimate. I always prefer 100 over a factor of 10, but a factor of 10 is sort of the bare minimum. So, for instance, if you were wanting to calculate the electric field around a wire and you planned on being 1 centimeter away from the wire, then that wire needs to be at least, let's say 20 centimeters long, because it's got to be 10 centimeters. If you're dead center, it's got to be 10 centimeters from that end, 10 centimeters from that end. Again, I would prefer more like 15, 20, 25, or even 100. So at 1 centimeter away, it'd be really great if it was 2 meters long. But again, if you look in the module, you'll see an extra credit called How Far is Too Far? And I highly recommend you do that. That one's not with Gauss's law, but it was done with Coulomb's law. But part of it you can do with Gauss's law because you're actually assuming that something's infinitely long, which means you can use Gauss's law. Now, the other symmetry is infinite planar. So again, if you have an infinite plane of charge, then you can use Gauss's law to calculate the electric field. So we're now going into, as I said, sort of like the transition from chapter 5, which was the last part of Newton's second law. Then chapter 6, we did gravity. And then chapter 7, we talked about work. And chapter 8, we talked about energy. And basically 7 and 8 is where we switch from doing physics based on forces to physics based on energy. And specifically, we define mechanical energy as potential energy and kinetic energy and stuff like that. And we can still solve the same problems, but for different variables, it's a little easier. And the beauty of it is because you're using energy, it's a scalar quantity. So that was the major advantage in going from chapters 5 and 6 to chapters 7 and 8 is now we could actually focus on non-vector quantities. So it made it a little easier. The same thing's going to happen. The same thing's going to happen now. We're going to switch from all these vector quantities and go to something called the electric potential. That's different from the electric potential energy. Electric potential energy is an energy and it's measured in joules, whereas electric potential is measured in joules per coulomb, and that's called a volt. So that's what we're studying now. And your book, chapter 23, starts off with the name of the title, the name of the chapter being electric potential. Section 23.1 is electric potential energy and potential difference. 23.2 is the relation between electric potential and electric field. 23.3 is electric potential due to point charges. 23.4 is potential due to any charge distribution. So that stuff that we did, the integrals, for instance, to integrate Coulomb's law, we can now do that with, or we'll be able to do that with electric. Oh, sorry, I don't know why I can't stop yawning. We can now do that with electric potential, so it's a scalar quantity and a lot easier. And guess what? We'll teach you that there's a way, once you have the electric potential, you can easily get back to the actual electric field. So we're going to learn that as well. We're going to talk about, this is mostly for your reading, equal potential lines and surfaces, but that's completely consistent with what we did in the electric field mapping lab. So hopefully y'all have already done that. Potential due to electric dipole and the dipole moment. We'll be talking about that. Section 23.7 is E determined from V. So that's what I was telling you about, that we will recover. Section 23.8 is electrostatic potential energy and a new unit of energy called the electron volt, which is super, super convenient when you're dealing with things on the size of atomic quantities like electrons, protons, neutrons, that sort of thing. There's a section called digital binary numbers, signal voltage. That's stuff that I highly recommend you read, especially if you're going for double E or computer engineering or software engineering or hardware engineering. I definitely recommend you reading that, as well as 2310, which is on TV and computer monitors, and 2311, which is on electrocardiogram, EKGs and ECGs. So those are all optional sections, 23.9, 23.10, 23.11. Those are optional in that there might be some problems that we could, that you'll see as examples, but I'm not in general going to ask you to solve those. So now that I've given you an intro to what the chapter 23 is about, of course, you should always start off by reading your chapter opening question and guess an answer. And, think long and hard about it to make sure you have an idea of why you're thinking that. And then wait, because we'll get to a new section in this chapter where you'll finally get the right answer to that, and then you can figure out what your error was or whether you got it right or not. So with that in mind, we're going to go on to electric potential difference. If you actually look in your ebook, I have selected some quotes that are important and highlighted them. So the very first one, it says, we saw in chapter 8 that the charge and potential energy, we saw in chapter 8 that the change in potential energy between any 2 points, A and B, equals the negative of the work done by the conservative force on an object as it moves from point A to point B. That's what we're going to use. So again, I'm going to state that the change in potential energy between any 2 points, A and B, equals the negative of the work done by the conservative force on an object as it moves from point A to point B. So that's our opening call for us to start thinking about electric potential and how we're going to calculate it. So what I'm going to write down, and I'm going to go ahead and share my screen with you guys now. So let's do share screen, iPad. Pull this down, bada bing, bada boom. Zoom Williams iMac, got it. Okay. So what we're going to say is delta U which is actually UB minus UA. So what I mean by that is the potential energy at point B, which is the final position, minus the potential energy at point A, which is the initial position. That is equal to the negative of the work done, and this is the work done by the conservative force. Oops. I spelled done like dough. I don't know what that was. But anyways, done by the conservative force. Okay. So what that means is delta U, oops, stop writing in blue, in red. So what that means is delta U, which is again UB minus UA, is equal to the negative of the work done, and work is F dot DL. Okay. This is what I've told you before if you had me in the past, but this is called a line or path integral. Now, the cool thing about a line or path integral is a lot of times you can do it, you can often do it 20 times and never realize that you're actually doing a line integral or a path integral. But to actually do it consistently right, you really need to understand what a line or path integral is and how we go about it. So just like when I covered a surface integral, remember the main thing I told you was that the integral of E dot dA was a surface integral, and I had to make sure I evaluated E and the dA on the surface. So in other words, E might have a function of X, might be a function of X, Y, and Z. If you have an equation that gives you the equation of the surface on which you wish to integrate, then you can take that equation, which will be in terms of X, Y, and Z, and for instance, solve it for X in terms of Y and Z. And then everywhere in your electric field where X appears, you can replace it with that function of Y and Z. And then by doing that, you've now established that the electric field that you're integrating is in fact on the surface. The same thing can happen with the dA, which could in principle have, specific coordinates X, Y, and Z, and that sort of thing. The same thing goes on now. We've got a path integral or a line integral. So we need an equation for the path that you're going to integrate along, like y equals x squared. And you could also say that y equals x squared. And then if you had, for instance, a force that depended on x and y, now what you do is take the y and replace it with x squared everywhere. And then you're filling the bill of making it a path integral or a line integral. So that's sort of what it is. But that's what we're working on now is we're working on the integral of f dot dl. And what I would like to do is show you exactly what that turns out to be. So for instance, if we take a case that we've already considered, let's look at, for instance, we covered parallel plates. And let's say this plate has a surface charge density of positive sigma. And let's say this plate over here, and I'm assuming they're really, really close together, but I have to draw them with a big gap just so that we can see what's going on between them. What I'm going to do now is I'm going to create a coordinate system so I can make some sense of where A and B are in terms of coordinates. So what I'll do is I'll put my x-axis right there. I'll put my y-axis right there. And what I'm going to do is I'm going to call this little spot right here, I'm going to call that point A. And then I'm going to call this one point B. Okay. So the trick with integrating or doing a path integral or a line integral is you've got to remember that you've got to use either the DL, that guy right there, or you've got to use the range of integration, these values right here. One of those two things has to specify which direction you're going. So for instance, here I said I'm going to go from A to B because that's clearly what this integral is suggesting, because delta U is UB minus UA. That means I'm going from A as my initial position and B as my final position. So I'm actually going from A to B here, and that means I'm actually going in the negative X direction. So I can either indicate that I'm going in the negative X direction by saying DL is going to be equal to, so let me write this down, either DL is equal to negative dx I hat, or I can say the integral is going to integrate from x equals d to x equals 0. One of the two. I can't do both. The other one just is going to have the idea of it going in the positive coordinate direction. So what I've also said here, even though I didn't stress it yet, is the distance between these plates is d. Okay. So that's what we're going to do. Now, what is the electric field in here? Well, we worked this out before. We know that the electric field inside is sigma over epsilon naught. And of course, it points in the positive X direction because it points in the direction that a positive charge would go. And since the left plate is the positive one, it wants to go from the left to the right. So I'm going to say the electric field is equal to sigma over epsilon naught. And that's my electric field in between. So now I can go ahead and calculate for this particular object, delta U, which again is equal to UB minus UA, is equal to the negative integral of, now I'm going to say sigma over epsilon naught I hat, there's my E, and now I'm going to dot that. This time I'm going to choose this version. So I'm going to let my differential path element, my DL, I'm going to let that indicate the direction of integration. So I'm going to write negative dx I hat. And since I did that, then my job is just to go from small x to large x. So since I chose this to specify direction, the range of integration is supposed to go from low to high. So what that means is, in this case, I'm going to go from x equals 0 to x equals d. So notice in this case, I'm actually going from x equals 0 to x equals d. That tells me what direction I'm going. And that's not technically the direction I'm going. I clearly did not go from x equals 0 to x equals d. I went the opposite way. But the rule was, since I chose the opposite way to be indicated by the DL, and you see that by the negative sign, the integration has to go in the positive coordinate direction, and that fixes everything. If I end up doing both of them, then I'll end up being off by a negative sign. So now I'm going to go ahead and go back to finishing this integral. I'm going to say these two negatives make a positive. I'm going to say sigma over epsilon naught is a constant. And now I've got the integral from 0 to d of, now I'm going to have just plain dx, and then I have I hat dot I hat. again, making use of the fact that a dot product is what we call a linear operator, and therefore I hat dot I hat is 1. And with this in mind, I should get sigma over epsilon naught times x, and then x is going to be evaluated from 0 to d, which finally gives delta u, which equals ub minus ua, is equal to sigma d over epsilon naught, because when I let x equal d, I get d, and when I let x equal 0, I get 0. So notice that came out to a increase in the potential energy. So note delta U is greater than 0, implies delta U implies, let's do a different thing, U increased. Now, what we were imagining doing was going from a negative place, in other words, the negative charge of the right-hand plate, to a positive place, the positive charge of the positive plate, right? That should be an increase in potential energy, meaning that if you did have a positive point charge and you stuck it at A and you let it go, it would move to B on its own. Okay, so that would actually, excuse me, it would not, excuse me, I said move to be on its own. That's not right. I apologize. So yeah, if I stuck a positive charge at A, which is right next to the positive or right next to the negative plate, it's actually going to be attracted to that negative plate and want to stay there. So it would actually physically take some work for me to push it to the left over to D. The fact that that came out positive is a good indicator that I did this correctly. And that's the whole point of doing path integrals and line integrals. When you do them right, they will have the right sign and all that stuff. So now what I'm going to do is show you how I would have done it if I chose instead to do my range of integration to indicate the direction I went, as opposed to my DL. So another way. Now this is one of the simpler cases where I don't really have to do anything specific about the line I chose. The line that I chose was the line y equals 0, but because I have no y appearing in the integral, I don't have any way of implementing that. But the fact that this electric field happens to be the same everywhere between the plates means any path probably would have done the same thing. But now I'm going to do it another way. So I'm going to say delta U is equal to UB minus UA, which we decided was the negative integral of E dot dl. Now the electric field is still sigma over epsilon naught pointing in the I hat direction. Now this time I'm going to let dl just point in the positive coordinate direction. So that means I'm just going to say dx I hat like that. But now, because I'm doing that, I have to specify the direction of integration by putting the range of integration in the proper order. So I'm going to say I'm going to integrate from x equals d to x equals 0. Okay, so this is the other choice. I'm going to do this right here. See another way. Okay, so that's just to, so you'll see it later and realize, oh, that's what he was doing. He was doing it again, but this time in a different way. Now notice I can go ahead and do the dot product, but the negative is going to stay there this time. And I'm going to get a sigma over epsilon naught because that's still a constant. And I'm going to integrate from d to 0 of dx I hat dot I hat, which again we know is just 1. So ultimately, I end up getting negative sigma over epsilon naught, and the answer of the integral is just going to be x, which I'm going to evaluate at 0 and then at d. So this is negative sigma over epsilon naught times 0 minus d, which is in fact equal to positive sigma d over epsilon naught. And this confirms the original result. Now, what does that physically mean? So this quantity that we just calculated was the change in potential energy, okay? What we're trying to do is we're going to come up with something a little different. So remember, we first off started with Coulomb's law, where F is equal to Q1, Q2 over 4 pi epsilon naught R squared, right? And then we said, well, we didn't like the action and the distance problem. So we imagined that one of the charges, Q1 or Q2, for instance, creates an aura around itself, and then the other charge feels the aura. And then you're not talking about action at a distance, because we're actually physically imagining that one of the charges altered the space around it, giving it what we call an aura. And then the other charge got in that space and was affected by it. So if we go on that assumption, then we should be able to realize that maybe there's a parallel to it when I switch from potential energy, which is U, to this new electric potential. And in fact, you'd be exactly right. So what we did in going from the force to the electric field was we divided the force formula by one of the charges, specifically by the charge that we would say is feeling the aura. So if we now think about potential energy, and instead of thinking about potential energy, we want to talk about what's called the electric potential, then what we'll do is we'll say that the electric potential, VB minus VA, which is the electric potential's change in going from A to B, that's going to be the work divided by the charge that felt it. Okay. So that's where we get the idea of electric potential. We also discovered something else by doing this integral. I'll go ahead and mention it here. Oops, lost it. In a uniform electric field, of strength E, the change in potential energy is just now. What we're going to do is I'm writing exactly what the book has. So we're going to say delta U, which is UB minus UA, is equal to the negative of the work done, which, remember, the electric field was in fact pointing to the right, and we ended up getting a positive quantity, and you could actually account for that by saying negative Q times E times D, because putting the electric field pointing to the negative direction would give you the actual negative. Or you could just think of it as we integrated F, which equals the, ooh, maybe that's the problem. That's what I did. Okay, this still works, but really what I just did was calculate the electric field. God, that was a really bad mistake. Sorry, everybody. I completely jumped ahead, and I actually just wrote down this. What I was really going for is this. Let me rewrite this and try to regroup. I'm so, God, this is bad. I'm so sorry. But anyways, yes, delta U, which is UB minus UA, is the negative of the work done, which equals the negative integral. Now, here's what everything that I did writing all this is completely right. Okay. Now, the problem is if I wanted the put this in terms of the electric field, then I got to remember that the force is equal to charge times the electric field. That's the part that I sort of just haphazardly skipped. Okay. And I skipped it because I just grabbed the formula. I was flipping through the pages on my ebook and just grabbed the formula and wasn't paying close enough attention. I apologize for that. That was just screwed up. But what you can see now is this is going to become the integral of Q times E dotted with DL. That still works. So now we can carry out the whole thing, only now I've actually got a Q in play. So I'm going to say this is negative Q times the integral of E dot DL. Now I'm going to apply the principles that I just said about a line or surface or line or path integral. I'm going to say negative Q. And since the E is actually a constant, that's what it means to be a uniform electric field. So E is equal to a constant vector, okay? So what I'm going to do is I'm going to write that constant vector as, oops, let me go back to green since I was using green. I'm going to write that constant vector as E times I hat because it did point to the positive direction. And now I'm going to dot that. This time I will use again the differential line element to indicate the direction. So I'm going to say negative dx I hat like that. And that will give me positive QE times the integral of dx and then I hat dot I hat like this. And of course, since I've chosen the show the direction with the negative sign on the DL, that means I should have also chosen to go in the positive coordinate direction, which is from x equals 0 to D. So 0 to D, and this, of course, because this is 1, this, of course, is going to give me Q times E times D, and that's exactly what they were trying to show you. Okay, so the change in potential energy is basically QED, or if they wanted to put it in terms of the original electric field, it'd be the negative of the QED. So alternatively, let's say alternative way. So I'm doing the same thing now that I just did, but now I'm going to do it with letting my range of integration show the direction I'm going. So I'm going to say delta U is equal to UB minus UA is equal to the negative integral of F dot DL, which is going to be the negative integral of QE dot DL, which is going to be the negative Q times the integral. Now this time I'm going to integrate from x equals D to 0 because that's the actual real direction I'm going. And the electric field is just going to be E, or excuse me, I'll take off that little vector symbol, E times I hat because it points to the right. And then I'm going to dot this with just dx I hat like that because this is the positive coordinate direction. So that's why that one's that way. And this shows direction, where in the previous way, this showed direction. And this is the positive coordinate direction. Okay, so that's the two differences. Not a big deal. We can carry on now and say, I'm going to get negative Q times E times the integral from D to 0 of dx times I hat dot I hat which again is 1. And this time I get negative QE times 0 minus D, which gives me positive QED again. Okay. So that actually is a way we can work it out. The main thing is that I'm trying to get with this line that I wrote down here is when you have the electric field as uniform, then the voltage, or excuse me, the change in potential energy will just be the force times the distance. And the force is QE and the distance is D. So the QED is really what I'm trying to get out of it. Okay. Anybody have any questions on that? All right, so now I'm going to introduce you to the idea of electric potential. So this is what I was talking about, where we went from Coulomb's law, where we had F is equal to, let's call it big Q over 4 pi epsilon naught R squared. And we ended up going to E is equal to big Q over 4 pi epsilon naught times R squared. And the reason we did that is we basically said let E equal the limit as Q approaches 0 of F over Q. Okay. Now in practice, I'll write it like this. So I'm going to say in practice, you pretty much always have F is equal to QE, meaning sort of we can ignore limiting process. Okay, so that's what I mean by just writing F equals QE. So what we did to go from the force to the electric field was we divided by charge. So now what I'm going to do is I'm going to say delta V, which is VB minus VA, is equal to the negative of the work done divided by Q, which equals the negative of the integral of F over Q dot DL, which equals the negative integral of E dot DL. And that's the most important part. So let me restate that. Delta V is equal to VB minus VA, which equals negative W over Q. And that is equal to the negative integral of E dot DL. Okay. The main thing is you got to remember that the force, the work is being done by the force in calculating this, not by you. That's why the negative has to be in there. So this is the new important result that we're going to need. Anybody have any questions on that? So ultimately what that tells us, if you look a little further, you can see that V, let's say VA, is actually going to be UA divided by Q. And that lets us see that the units of voltage is equal to the units of potential energy divided by the units of charge, which is equal to joules per coulomb, and 1 joule per coulomb is defined to be 1 volt, which can be abbreviated 1 with a capital V. So this is another important fact that we're going to make use of. So now we know what the units are, and we know the origin of the idea of a volt. A volt is literally a joule per coulomb. So when you have a 12-volt battery, what that means is that 12-volt battery can potentially give a 1 coulomb charge a potential energy of 12 joules. And remember, a joule is about as much energy as required to lift a really good, juicy, red delicious apple, the brand or the actual species of apple called red delicious. So if you actually have a really good, healthy, juicy one, if you pick it up from the floor and raise it to the height of a common kitchen table, that takes about 1 joule of work. So imagine a 12-volt battery actually bringing a 1 coulomb charge, which, by the way, a coulomb of charge is a butt ton of charge, can bring it up to a energy of 12 joules. So that's basically, taking something as heavy as a red delicious apple and lifting it up to the height of 12 desks stacked on top of each other. Now, if you imagine that 1 coulomb charge is probably more likely to be on something very much smaller than a kilogram, then you can see that it would lift that even higher. Now, what I want to tell you is something else that I actually highlighted, and actually it looks like it might not be sharing this with you, so I'm going to make it share with you. No, guess it isn't. Okay. It says, note that electric potential, like electric field, does not depend on our test charge Q. So when I divided out that Q, that was sort of the test charge that we were talking about. V depends on the other charges that create the field, not on the test charge Q. Q acquires potential energy by being in the potential V due to the other charges. Anybody have any questions on that? All right, so I'm sorry about getting this initial thing screwed up here. Technically, all that was really missing was because I did an integral of f and didn't actually realize or didn't actually make the change that f is supposed to be equal to QE. I did that, but without putting the Q. So that means I needed a Q right there, which would have been right there, which would have been right there, which would have been right there. Okay, actually, I better take that one off. So you can see where all that comes out. And in fact, it would also be right there, right there, right there, right there, and right there. So that actually corrects it. If you just take that plus arrow, or excuse me, that arrow, and put in a positive Q charge in there, then that will fix everything and give you a result consistent with that. Again, I am very sorry for screwing that up. That was, I guess I just wasn't paying attention, but that was a bad screw up. So sorry about that, folks. All right, now that we have that, we have some idea of what the idea of a voltage is. A voltage is a certain amount of potential energy per unit charge. But think about it this way. If we consider a special case, which I'm going to do now, let's go back to our parallel plates that we've discussed before. And I'm going to take this and say, this is one parallel plate. Whoa, Nelly. Okay, like that, like that, and like that. Now, what I'm going to do is I'm going to imagine that is actually packed full of positive charges. So I'm going to put a positive charge here, positive charge here, positive charge here, and a positive charge here. And now I'm going to draw another plate right here. Now this time I'm going to get a negative charge, a negative charge, a negative charge, and a negative charge. And the fact that they're the same on both sides is just trying to show, hey, these two have the same magnitude of charge per unit area. So this one, for instance, would be plus sigma, and this one would be minus sigma. Now, this is very much like we started off with, but what I want you to understand is this creates an electric field. And the way we picture electric field lines is they actually begin on positive charges and then die on negative charges. And you know from your field mapping lab that this is pretty much what happened with the electric field of two parallel plates. Now, in principle, as you got near this end, what would happen is the electric field line would leave the conductor perpendicular. So that's why I drew that little box there. And then it's going to bulge out and then start to bulge back in and come back to the conductor perpendicular again. So that's how the electric field is going to behave at the edge of the parallel plates. Same thing here. It's going to go up, reach some maximum distance out, come down, go like this. And again, this is perpendicular and this is perpendicular. Okay, but that's basically how the electric field is going to be. Now, check this out. We're going to imagine a positive charge right there. And a positive charge, if we imagine moving it over to here, then we'll get a positive charge over here. Now, this is a positive charge next to a positive plate. And that means it has a very high potential energy. Positive charge near a positive plate implies U is high. And remember, U is potential energy. Now, over here, we have a positive charge near a negative plate. And this implies that U is low because the positive charge is actually attracted to the negative plate and it's quite comfortable there. Now, if we take into account the fact that V is equal to U over this Q that we're dealing with, then we see the high potential energy corresponds to high electric potential. Similarly, this corresponds to a low electric potential. So notice I'm saying electric potential without the word energy. When I leave off the word energy, if I just say potential or electric potential, I'm talking about voltage. Okay, so potential and electric potential means voltage, whereas potential energy implies joules. Okay, now let's look at doing the exact same thing, only this time we'll do it with a negative charge and we move it over here like that. Now, when we do this, and I'm going to use a different color, let's say the different color I'm planning on using is going to be this dark blue. God darn it. So this dark blue that's going to correspond to a place at which we have a negative charge next to a positive plate. And remember, opposites attract, so this negative charge is going to be quite comfortable. So we're going to say this is a low potential energy. Okay. But V is equal to U over Q implies V equals a low number divided by a negative number. And of course, that means we get less than 0. Here I have a high potential energy. Because that time I have a negative charge next to a negative plate. It's not comfortable at all there. So this implies that V, since V is equal to U over Q, we're going to have a high number divided by a negative number. So again, we're going to have a quantity that's less than 0 in principle, but the main thing is it actually has a higher electric potential. So I'm going to say, but V at, but V, let's call this point A and point B. So VA is actually, I don't want to say that. I'm going to say VA is actually greater than VB. And the reason all this is going this way is because it turns out that electrons go from low voltage to high voltage. Electrons actually all negative charges go from low voltage to high voltage. Positive particles go from high voltage to low voltage. So these little things that I'm writing here are really what's critical to your understanding. I can't tell you how many times that I've gotten into some kind of philosophical conundrum trying to figure out whether the voltage change is positive or negative, and the signs, which in principle, if you stick to the signs of all the equations that we're using, like equation 23.1, 23.2, and all that stuff, they will give you the right answers. But if you're not really careful with that, you can screw it up and get the wrong answer. And what you need to understand that is these principles I'm putting down, which is because the electric potential is the potential energy divided by charge, then you're going to get a negative particle going from a low potential to a high potential. Again, I said potential without the word energy. So that's from a low voltage to a high voltage. So negative particles travel from low voltage to high voltage on their own or spontaneously, as we learned in the chapters on thermodynamics. And positive particles spontaneously go from high voltage to low voltage. So just keep that in mind. That should help you. Now that we have all that worked out with some, hopefully some understanding, we can ultimately make some conclusions about stuff. I've already given you, for instance, that delta U is equal to UB minus UA, which equals the negative of the work done, which equals the negative integral of F dot dl, and this has to be the conservative force. So Coulomb. So that's one of the equations that we have, but it's not that relevant because that's something we already knew ostensibly from chapter 7 and or 8. But now there's another one that says delta V, and actually I want to write this in blue as well, that says delta V, which equals VB minus VA, is equal to negative W over Q, which equals the negative integral of E dot dl. And this has got to be the conservative E field. Okay. And all of this led us to believe that VA is equal to UA over Q. So that's another equation that comes in handy. But we can also say VBA. Ooh, I want to do this in blue. Sorry about that. VBA, which is supposed to be what we call delta V, which is, notice the subscripts are final and initial. So this delta V is going to be VB minus VA, which is exactly what we had before. And that means that I've got UB minus UA over Q, which is equal to the negative of the work done in going from A to B again over Q. So you can see this is essentially the same equation that we just wrote, but hopefully you see that it's sort of specifying a little bit more of the details so you can understand what's going on. Any questions on that? So your book is asking a very specific conceptual question. Let me ask it, and I want you guys to hear me out. You got to listen to it, and then respond with your answer either by typing it in a chat or by just blurting out the answer. That's fine. Either way you want to do it's fine. So the question is, suppose a negative charge, such as an electron, is placed near the negative plate in figure 23.1. So in this figure at the top of the page here, that's essentially the same figure. So imagine that a negative charge like an electron is placed near the negative plate. So at point A is what I'm saying in this diagram. If the electron is free to move, will its potential energy increase or decrease? So the electron's free to move. We're putting it on the right-hand side, which I call position A. It's going to be free to move. So will it move to a place where potential energy increases or where potential energy will decrease?
Decrease.
Yes, it's going to decrease. Potential energy always decreases on its own. If you try to make something increases potential energy, you've got to put work into it. So you remember the old example of potential energy being M times G times H. And one of the often quoted things is about a turtle. If you walk up and find a turtle sitting on a fence post, probably the turtle did not get there on his own, right? Well, I like to use that because that's a common metaphor that people think about, but you can use it now in terms of physics and realize, wait a second, The turtle didn't get there on its own. So someone had to physically do work to lift the turtle up on top of the pole. And that turtle is not comfortable being on top of that pole. So that's the indicator that I normally tell my students means if you're not comfortable, that means you're probably in a high potential energy. So in the actual turtle going from the ground level to the top of the pole, it actually increased potential energy, and that doesn't happen by itself. The same thing happens with objects in nature. Particles, electrons, positrons, protons, all of these things generally move in a direction of decreasing potential energy on their own. Otherwise, they stay perfectly still. If you want them to move to a place where the potential energy is increased, something's got to do work on it. So does everybody understand that conceptual problem? I'm just going to tell you guys to read and understand. Example 23-1. Now, the general rule, and I told my students in face-to-face class this today, I just went through those sections of chapter 23 that we're going to cover and told you specifically which chapter section, subsections we were going to omit. So when you do that, when you look at a chapter and you know which sections are being omitted, what that should mean to you, and I mean this in all your classes, not just my physics class, but what that should mean to you is you better understand how to do every example in the subsections that were not omitted. And that means literally like take a screen or take a photo with your camera of just the actual statement of the question and maybe the figure if they gave you a figure, but only that, not anything telling about the solution, and then close your book and solve it. If you can't do that, you didn't learn that example well enough. So I need you guys to do that with every example. And that's sort of the lowest hanging fruit of preparing for a given chapter. So for instance, when you finish chapter 23, you should be able to work out every example from chapter 23, except for the sections that I told you to omit. So if you can't do that, then you're really not ready. You might have still been able to do pretty well on the face-to-face test, but it's going to get worse and it's going to be nearly impossible to do well unless you can do all those examples. So yes, I'm taking time to tell you explicitly, make sure you read over and can understand example 23-1, but that's a general instruction period. Anybody have any questions on that? Okay. Now, the good news about this voltage thing is life is a lot easier with this voltage thing. For instance, I can calculate the voltage due to a point charge, just like I calculated the electric field due to a point charge. Remember, that turned out to be Q over 4 pi epsilon naught R squared. And I could even put a vector symbol on it by saying times parentheses RP minus RQ, close parentheses, and then dividing it by the magnitude of RP minus RDQ. That would actually give me the vector quantity. On this case, it's even better than that because you don't have to have the vector quantity at all. You're going to get a Q over 4 pi epsilon naught R. Notice I didn't say R squared, and there's no vectorness associated with it. Another thing that this last equation tells you is that delta U is equal to, let's do this. I'm going to say Q times VB minus VA, which equals Q times VBA. So this is yet another version of the equation that comes in handy. And specifically, the reason I'm doing that is I want you to know of a new unit. So now that we have that equation, I'm going to say delta U is equal to Q VB minus VA. And let's say how much energy does a electron acquire in going from 0.00 volts to 1.00 volts. Okay. So what we know is the charge of the electron is Q sub E, which is the negative of E, which is negative 1.602. Dang it. My decimal did not show up very well there. So this is 1.602 times 10 to the negative 19th coulombs. That's the actual charge. So what I'm going to do is solution delta U is equal to Q times delta V, and Q is negative 1.602 times 10 to the negative 19th coulombs times delta V, which is VB minus VA, and I'm going from 0.00 volts to 1.00 volts. And that actually is taking the particle from the 0 voltage to the high voltage point, and that's actually the direction it wants to go. So we're actually going to get a decrease in potential energy because that's what electrons naturally do. But more specifically, what we get is negative 1.602 times 10 to the negative 19th joules. And we now define the quantity 1 EV equals 1 electron volt, which equals 1.602 times 10 to the negative 19th joules. So that's the unit of energy that we'll work with when we're dealing with electrons, protons, neutrons, atoms, things of that sort. So anybody have any questions on that new energy unit? Notice what I like about it is the E that I used in the symbol EV looks just like the symbol that we use for the charge of the electron. And the V, which is capitalized, looks just like the symbol we use for voltage. And in fact, it's exactly the formula. Q times V is the formula for energy. So U is equal to Q times delta V is built into the actual symbol of electron volt. So it's just a nice little thing that helps you keep track of some of your equations. If you ever forget, oh, the electron volt. Oh, yeah, that's right. I can multiply the charge times the voltage, and that'll give me the energy. Any questions? All right, so to give you some examples of various voltages, your book actually gives a table of some typical potential differences. So if you're talking about cloud to ground lightning, then what you're talking about is it's often the voltage difference between the cloud and the ground of on the order of 100 million volts. So 100 million volts is a big number. That's one followed by 8 zeros. So there's literally 100 million volts difference between the electric potential of a cloud and the electric potential of a ground. Sometimes the ground is the higher potential. Sometimes the cloud is the higher potential, or at least that's what I've read. I've never done any research in this area other than just reading books and so forth. But I know there's things they call cloud to ground lightning, and then there's arguments that I've read in various books that suggest that there's ground to cloud lightning. I'm not really completely sure about that. I know the books I was reading were written in the 1800s, so we might know quite a bit since then. So I'll just tell you that that's one of the things they argue. And to be honest with you, a meteorologist would be a better person to ask about that. But I'll just tell you that, yeah, 10 to the eighth volts is a reasonable amount of voltage difference between a cloud and the ground. A high voltage power line. So these are the ones that look like a human with no head, those big towers that you see running through the country. And it's like a big human, maybe wearing a skirt, but not, and having poofy shoulders, but no arms, right? And doesn't have a head, that weird little tower. Those things are often 100,000 volts to even 1,000,000 volts. And in fact, when you actually work on them, that's hazardous duty pay, and you can actually make pretty good money doing it. Like, it's not uncommon to get on the order of $100 an hour while you're doing that. But one of the ways you can service those is they drop you off on a helicopter, from a helicopter on the top wire. And being at, 1,000,000 volts sounds really dangerous, but in reality, it's not that dangerous because you're so high up. The only way that could be a problem is if you somehow, became one of the Incredibles, for instance, and grabbed a hold of the wire and then stretched your long, silly putty like leg down to touch the ground. If you did that, yeah, you'd probably explode in a violent explosion as a result of your body trying to carry so much amperage down to the ground. But as long as you're isolated from the ground and only touching things about the same voltage as yourself, then there's no harm to it. Now, obviously, if you're that high, there's a whole other problem that basically means, hey, if I fall, I'm going to die. So yeah, that's true, but that's why they pay you so much money. So yeah, that's another voltage that is common, is on the order of 1,000,000 volts, is the power lines that go through the country. A household outlet, we actually normally run our households here in America at 120 or 125 is what they call it. And it does actually vary. If you actually put a multimeter on the actual light socket, you're going to find that it's an AC light socket, but two, you're going to find the voltage ranges really from 120 to 125. And that's actually technically what we call a root mean square voltage. So they basically cover over one cycle, they calculate the average of the square of the voltage, and then they take the square root of that, and that's where they get the 120/125. It's more like, if, for instance, if we called it 125 and I multiplied that by the square root of 2, I would get about 177. So that's really what the peak voltage is. So when we talk about AC voltage, what we really mean there is, let's say, a voltage up here, and then a time axis here, and the voltage will actually run up, down, up, down, up, down, like that. And it runs back and forth from about 177 volts to negative 177. Now, I didn't draw that to scale like I should have. The t-axis is too high, but that's really what we're talking about in terms of what AC voltage is. And the root mean square voltage is on the order of 125 volts, which is voltage peak to peak divided by the square root of 2. We'll learn about that later, but I just wanted to give you an idea. So your book says household outlets are on the order of 100 volts. A flashlight battery, in fact, A batteries, well, AA batteries and AAA batteries, and C batteries. You probably have encountered D batteries. I see a lot less of those, but C, D, A, AAA, or excuse me, AA and AAA batteries, they're all roughly 1.5 volts. Obviously, the rectangular ones, and I highly recommend this, the rectangular ones that are only about that big, that go like in your smoke detector, and they have a little circle on one side, and then they have another little circle that's got sort of a barbed edge or something. Those two little circular probes on top are the positive and negative terminals of the battery. And that is a 9-volt battery. And I highly recommend you just taking your tongue. This is not going to feel good, mind you. Okay. You can take your tongue on a clean battery. Obviously, you don't want to just grab one out of somebody's toy or something. But with a clean battery, or one that you just cleaned, you can take and stick your tongue against it, and you will see that voltage is there. And that's actually a good way to test it. I just grew up doing that and I get a kick out of shocking myself or whatever. So do that. Uh, Resting potential across a nerve membrane. So when you're talking about neurons and stuff like that, or across, your ulnar nerve or your in ulnar neuropathy, for instance, or any of those other nerves, those are on the order of 1/10 of a volt. And when you're talking about potential changes on the skin, they're like 10 to the -4th volt, so 1/10 of a millivolt. That's not uncommon to what you'd read in an electroencephalogram. So basically, when they put the probes on your head and try to measure electrical signals in your brain, they're measuring on the order of 10ths of a millivolt. Uh, Voltage across for EKG is also on the order of millivolts. Okay. Any questions on those rough orders of magnitude for voltages? I'm just going to say, whoa, Nelly. I'm just going to say that whenever I try to type that, that does not work. So C table 23-1. Okay. Now let's look at this. Suppose an electron is accelerated from rest through a potential difference of 25,000 volts. Suppose is accelerated through a potential difference of, whoa, Nelly, 25,000 volts. So I'm going to say VB minus VA is equal to positive 25,000 volts. Okay. A, what is the change in potential energy of the electron? And then part B, assuming the electron is not relativistic, what is the final velocity of the E minus, assuming V0 is equal to 0? Okay. So solution. Oops. So delta U plus delta K is equal to 0. That's not normally the way I do conservation of mechanical energy. I normally do U initial plus K initial plus some other stuff is equal to U final plus K final plus some other stuff. But I'm doing it this way. So what I want to do is I want to apply this here. And what we're saying is the change in voltage, i.e. the final minus initial, I'm going from a voltage, say, of VA equals 0. That's one way we can look at it, to a voltage of VB equal 25,000. Okay. So that's what my VB and VA are. If I wish to do that, then what I need to do is calculate my delta U. Now, what we found from this equation right here, for instance, delta V is equal to delta U over Q. Okay. So in this case, I'm going to say delta U is therefore equal to Q times delta V. So for part A, the change in potential energy is negative 1.602 times 10 to the negative 19th coulombs. There's my Q times my change in voltage, which is 25,000 volts. And with that, I get 1.602 e to the negative 19 times 25,000. That gives me 4.005 times 10 to the negative 15th joules. So that's my change in potential energy. Though it's not that helpful because it's in a unit that is joules, but it's really hard to figure out what that means in terms of something like an electron. So an electron volt might have been a better result, in which case you would have said the change in potential energy. Oh, by the way, that's a negative. Uh, oops. You'd say the change in potential energy, therefore, is negative 25,000 electron volts. So you can see already how much easier it is to calculate change in potential energy that way. So there's part A. Now what I want to do is I want to assume that that change in potential energy is equal to a change in kinetic energy. Now notice it went from 0 to 25,000 volts, so that it actually went the direction it liked to have gone, and therefore it's going to do it on its own, and in fact is going to speed up. So what I'm going to do now is I'm going to take B, which is the chance for us to calculate the actual velocity, and I'm going to say delta U magnitude is equal to delta K magnitude. So I'm going to say that is equal to 1/2 mv final squared minus 1/2 mv initial squared. But remember, I said it initially started at 0. So I'm going to say that, oops, because of that, I'm going to say V final equals 2. Oh, darn it. I'm going to say V final is equal to 2 times the magnitude of delta U over m of the electron. And then I'm going to take the square root of that. So I don't have much room, so I'm going to read these words out. What I'm going to do is I'm going to take 2 times 4.005 e to the negative 15. Okay, so I said 2 times 4.005 times 10 to the negative 15th. So that's my 2 times the magnitude of my delta U. And now I'm going to divide that by the mass of the electron. And your book actually gives you the mass of the electron. I will tell you that the mass of the electron is 9.109 times 10 to the negative 31 kilograms. So now I'm going to take that 2 times 4.005 times 10 to the negative 15th. I'm going to divide that by 9.109 e to the negative 31. And that's going to give me 8.79 times 10 to the 15th. And I'm going to take the square root of that. Now, the unit-wise, it does work out, but you're going to see this is going to greatly exceed the speed of light because technically this is a relativistic calculation that we should be doing here. So I'm going to take the square root of that answer, and that's going to give me 9.37 times 10 to the 1, 2, 3, 4, 5, 6, 7. Oh, maybe not. 1, 2, 3, 4, 5, 6, 7 times 10 to the seventh meters per second. So at least it didn't exceed the speed of light, but it was certainly close to it. And it's certainly not correct to use that formula for the kinetic energy just because it's the non-relativistic formula. Anybody have any questions on that? All right, so that's a very typical, straightforward, easy question. And in fact, when you do the lab magnetic deflections, that's exactly the calculation we're going to be doing because we're going to have a metal plate that basically has a negative charge, and then directly opposite is going to be a positive plate that has, of course, a positive charge, and it's going to have a hole in the front, in the middle of it. And the positive charge is going to be all attractive to the negative electron charge. So the electron is going to aim towards it. But since the hole is in the middle of the plate, it's got no compunction to go up versus down, nor does it has any compunction to go left versus right. So it's going to go undeflected straight through the hole. And the kinetic energy that it's going to have at the end is given by Q times delta V, where delta V is the voltage difference between those two plates. And then we're going to run it through a magnetic field, and the magnetic field is going to cause the electrons to curve. And you'll actually see nice little blue lines that are the actual, well, it's the sign of the electrons going through, basically. So it's a physical indication that electrons are traveling along that blue line. And we'll see that in our magnetic deflections lab. Anybody have any questions on that one? All right. Well, let's go ahead and take a little break. Let's go ahead and it's 6:57 now. Let's take a break till 7:05, and I'll come back. We'll come back and I'll finish up some stuff regarding this voltage chapter. So everybody see me in about 8 minutes. I'm gonna step away for a second, but I will be back. I don't keep coming to buy your man. It tastes. All right, I'm back. All right, it's about time. So anybody have any questions on what we've done so far? So we've already given you one of the expressions. Your book is actually calling this equation 23-4. So just as a recap, I want to remind you that this equation, VBA, which is delta V, which is VB minus VA, that is actually equal to the negative integral of E dot DL, and we're supposed to integrate it from A to B to do that. So that is in fact exactly an equation I already gave you, but your book is calling this equation 23-4A, and that's what we're going to use. Now, in principle, you can actually calculate what that is. We've already figured out that for a uniform electric field, we end up getting E times D, where D is the distance you moved. And it actually turns out to be a negative E times D, but I usually don't pay any attention to the signs. I always use the actual understanding of the voltage versus positive charges versus negative charges to figure out what the sign should be, just to keep me from making careless mistakes with signs and stuff like that. So anyways, in light of that, if you actually realize that VBA could equal, for instance, negative E times D, then that tells you there's another unit for the electric field. And that unit for the electric field would, of course, be the unit for volts divided by the unit for distance. And therefore, we can now see that the units for the electric field are not just newtons per coulomb, but a much more convenient unit of 1 volt per meter. So that's a whole new unit that's super helpful. For instance, if we talk about epsilon 0 is equal to 8.85 times 10 to the negative 12th coulomb squared per Newton meter squared. Well, with this in mind, you could realize that that is actually equal to 8.85 times 10 to the negative 12th. And then we could say, if I took that coulomb squared and made it, or actually if I took one of those coulombs and made it in the denominator as opposed to the numerator, I would get coulombs over Newton meters times meters. Oops, let me do that a little better. Newton meters times meters over coulomb. The reason why I do that is now I see that I've got 8.85 times 10 to the negative 12th coulombs per. Now a Newton times a meter is a joule, so a joule per coulomb is a volt, so that's a coulomb per voltmeter. So that's a whole nother unit you could use for the epsilon 0 as opposed to coulombs per Newton meter squared. That comes in handy sometimes. But the main thing is we can now see voltage or electric field as a change in voltage over distance. And in fact, we're going to learn that, as I told you, this nasty 23-4A is a integral that you have to compute, and that allows you to take the electric field and get from it the voltage. Well, guess what? If you have the voltage, you can actually get the electric field. And the equation for that is E is equal to the negative gradient of V. Now, the gradient is a vector operator. And what do we mean by that is I'll put the negative out in front. And what I'm going to do is I'm going to write I hat partial with respect to X, leave a space, plus J hat partial with respect to Y, leave a space, plus K hat partial with respect to Z, leave a space, and then do V. So from this, you can see that I get negative partial of v with respect to x I hat minus partial of v with respect to y j hat minus partial of v with respect to z k hat, which I guess I'll write it this way. I'll say this implies that e sub x is equal to the negative derivative of v with respect to x. E sub y is equal to the negative derivative of v with respect to y. And of course, the z is the same way. So this is a whole nother thing that we can use. In fact, I'm going to have more to say about it a little later when I tell you some neat mathematical facts that come as a result of this conservative electric field, conservative forces, stuff of that sort. So anyways, anybody have any questions about that new idea of how we can actually get the electric field from a voltage? So if we can actually compute a voltage in terms of X, Y, and Z, we can now do a series of derivatives and multiply by -1 and ultimately get the electric field out of it. So anybody have any questions on that? Okay, no, my chat screen is still there, so we're good. Okay. Uh-oh. Don't know what happened. See if I can do it this way. My whole screen just sort of stopped everything, and I don't know what's going on. Are you guys, can y'all hear me still? I don't know. Okay, good. I was afraid my computer crashed. All my windows slipped out the outside, and now they're acting like I can't control them. Oh, finally, came back. Okay. I don't know what happened or why this is doing the thing it is, but it did do something. I think I accidentally opened up an app that's not supposed to be open. Are y'all still looking at my iPad page?
Yes.
Okay, cool. Good deal. All right. Looks like we're all up to snuff now. So for instance, let's look at a case. This is going to be very much like a example in your book. What I'm going to say is two parallel plates are charged to a potential difference. So let's say, darn it, I hate it. I'm very one does that. Two parallel plates my computer did try to crash. Okay, so two parallel plates are charged to produce a potential difference of 100.0. Now, here's a question. I just said two parallel plates are charged to produce a potential difference of 100. What units am I going to end that 100 with? There's two choices here, a joule, 100.0 joules, or 100.0 volts. Anybody have an idea what the right answer would be? Yes, that's right, Ethan. I wanted to make sure y'all remember that when I say potential difference, but don't include the word energy, then you understand that that means electric potential difference and therefore is a voltage. So two parallel plates are charged to produce a potential difference of 100 volts. If the separation between the plates is, let's say, 0.010 meters, then what is the magnitude of the electric field between the plates. So we basically have what I've been hinting to you guys about: a positive charged plate and a negatively charged plate. They're parallel to each other. They're uniformly distributed charges over the surface. They're separated by a distance d. Specifically, what we're going for here is we want to know the electric field. What we know is the delta V is equal to 100.0 volts, and we know the D is equal to 0.1010 meters. I think that's what, yeah, I'll do that. That's basically about 10 centimeters. And what I want to know is what is the electric field? Now, since it's the parallel plates, we know that the electric field is uniform. Our E is a constant. And that delta V is equal to E times D in magnitude. So E is going to be just equal to delta V over D. So I'm going to say the delta V is 100.0 volts, and I'm going to divide that by D, which is 0.10 meters, which is really 1 over 100. So this is going to be 100.0 volts divided by 1 divided by 100, and I'll say 1.0 divided by 100 meters. And now you can see that by dividing by a fraction, you have to multiply by the reciprocal. So I'm going to get 10,000 volts per meter is the actual electric field strength. And I'm completely throwing caution to the wind and ignoring sig figs and all that good stuff. But technically, we should have 4 sig figs. 1, 2, 3. Oops. 1, 2, 3, 4. So maybe this one digit, darn it. Maybe this one digit at the end is not a sig fig, but that's it. Anybody have any questions on that? The coolest part about that, hopefully you understand, is that the electric field is now talking about having measurements or units of volts per meter. So if you talk about volts per 0.001 meters, then that would be 10,000 divided by 100. So that would give you basically 100 volts per 0.001 meter. So you could go 0.001 meter to the right of one of the plates, and that would be a voltage change of 100 volts. And then go another 0.0 meters, that'd be another 100 volts, so on and so forth. So that's a nice way of thinking about electric field strength as being in volts per meter, because every time you go another meter, you change the voltage by another, in this case, 100 volts over 0.01. Anybody have any questions on that? All right, now what we want to do is determine the potential at distance r from the center of a charge conducting sphere of radius r0. So determine the potential at a distance r from the center of of a charged conducting sphere of radius r. For A, let's say R is less than big R, and then say B, R is equal to big R, and then let's say C, R is greater than R. Okay. The total charge on the sphere is Q. So how are we going to work that? Well, what we know is VB minus VA, which is really just delta V, is equal to the negative integral of E dot dl from A to B. Okay. Now, for a actual point charge, what we know is the electric field is given by Q over 4 pi epsilon naught R squared R hat. That's the electric field, and that's got to be dotted with a DL. So what I'm going to do is I'm going to imagine that I have the charge, let's say right here. See if I can draw a circle, or see if I can get this to draw a circle nicely for me. I did. Okay, and now I'm going to say that's at the center of the circle is the origin, and Z is right here, and this distance is R. And what I want to do is I want to imagine where the voltage might be, for instance, 0. So if we go way out here, some ginormous distance to about infinity, V should be equal to 0. So that's sort of the plan that I have cooked up here. So what I'm going to do is I'm going to integrate along a radial line, which of course being a radial line, that means DL is going to be parallel to R hat, either in the negative direction or the positive direction. And what I want is I'm going to do it from two different positions. So just as a check, I'm going to say VB, oops, forgot I was writing in red. I'm going to say VB minus VA, which is equal to delta V, is equal to the negative integral of Q over 4 pi epsilon naught R squared R hat. And then I'm going to have that dotted with, as I was starting to write over here, I'm going to have that dotted with my path. Now, what I'm going to do is I am ultimately going to say that RB is my endpoint. So I'm going to say from RA to RB. Now I've indicated the actual direction I'm going. I'm going to go from RA to RB. So I'm just going to point my dr vector or my dl vector in the positive coordinate direction, which is going to be dr r hat, which is the same thing I'll put right here. Okay. Now this becomes the negative Q over 4 pi epsilon naught integral from RA to RB of, now what we have is dr over r squared times r hat dot r hat. But r hat dot r hat is just 1. So I get the integral of r to the negative 2, which would be negative r to the negative 1. So that's going to give me a Q is going to become positive. So I have a positive Q over 4 pi epsilon naught. And I ultimately just get 1 over R. I've already taken care of the negative, but now I have to evaluate it from RA to RB. So this delta V, which again is VB minus VA, is going to be Q over 4 pi epsilon naught times 1 over RB minus 1 over RA. Okay. Now, what I'm going to do is let's do it this way. Let RB go to infinity, which will imply V goes to 0. Okay. So what I'm saying is the voltage at B would be 0. So that means right here, I'm going to say 0 minus VA is equal to Q over 4 pi epsilon naught times the limit as RB approaches infinity of 1 over RB minus 1 over RA. And of course, this now gives you that VA is actually equal to, notice the negatives that appear on both sides because this quantity right here goes to 0. And then I'll have a negative VA is equal to negative Q over 4 pi epsilon naught R. So finally, I can say VA is equal to Q over 4 pi epsilon naught RA. And that's an actual answer. So if I wish to consider, for instance, for part A, for instance, R being, what did I write? R is less than big R, then I actually have to compute what it is at R smaller than big R. Okay. So we've got now a formula that will come in handy. VA is just equal to that. So that's sort of like Coulomb's law for a point charge. Remember, we had Coulomb's law for the electric field is Q over 4 pi epsilon naught R squared, and it points in the R hat direction, or basically RP minus RQ direction. Now I have a scalar electric potential V sub A, which is Q over 4 pi epsilon naught R, and that's the scalar quantity. Yeah. So if I wish to know further exactly what these quantities are, I've gotten this. If I wish to calculate the case for R less than R0, then what I'm going to do is figure out what the voltage is actually at, I said R0, at capital R. So V at R implies V is equal to Q over 4 pi epsilon naught R, like that. And then since this is a charge conducting sphere, that means the electric field inside the sphere is 0. It's also electrostatic. Implies that E equals 0 inside. So if I want to take V at R greater than R, then I'm just going to have V at R greater than R is just equal to Q over 4 pi epsilon naught R. That is what I called the answer to part C. Actually, let me change colors. So this is the answer to part C. if I wanted at V at the R, then I'd say V at R is equal to Q over 4 pi epsilon naught R. And that's my answer for B. And then finally, my answer for A would be, now I'm going to say V, let's say V at R, or let's say V at R less than R minus V at R equal to R is equal to the negative integral from R to R less than R of 0 dot dl, like that, because the electric field is actually 0 inside, and that's going to give me 0, which means the voltage inside is just going to be equal to V at R less than big R is just going to be equal to V at R equal to R, which equals Q over 4 pi epsilon naught R. So that's the answer to part A. I'm sorry it looks so small in there. I didn't realize I was going to take up so much page. But you see it's 4 pi epsilon naught capital R in the bottom. Anybody have any questions on that one? Now, I will tell you, and your book took the time to tell you this, so I'm going to go ahead and tell you, read and understand example 23-5. And what we're going to learn is that E breakdown, this means the voltage at which air becomes a conductor. Or I say a voltage, the electric field strength at which air becomes a conductor is equal to approximately 3 times 10 to the 6 volts per meter. So what we mean is if you actually have a voltage of 3 million volts and a 0 voltage within 1 meter of it, then lightning will strike from the 3 million volt object going to the 0 voltage object. Okay. In other words, a 3 million volt difference can span a air gap of 1 meter. So in that case, you're literally not even safe by being a meter away from 3 million volts, because if you're grounded, your voltage is 0, you walk within 1 meter of a 3 million volt wire, then the air looks like a fine conductor to the actual high voltage wire that you walk next to. And in fact, lightning will find a way to go and hit you. Okay. In fact, Tesla wore all through his life, when he started doing all these cool demonstrations and stuff and experimenting all the time, he was already like 6'5", 6'6", and weighed about 82 pounds, I think. Actually, probably weighed, close to 100. So not very much for a 6'5", 6'6" guy. But he walked around on 6-inch tall cork bottom shoes, specifically because the cork, C-O-R-K, was an insulator and would insulate him from ground. So he could readily grab, for instance, 3 million volts. And that maybe 3 million volts is a little bit high, but he could grab a high voltage and not be concerned about the completing the circuit to ground, because he had a good 6 inches of cork protecting him. The breakdown voltage for cork is a whole different number than 3 times 10 to the 6 volts per meter. So the electric field breakdown is the volts per meter in which air becomes a actual conductor. So anybody have any questions on that? Now, what we see is from this, the electric field is equal to Q over 4 pi epsilon naught R, whereas the voltage from that same charge Q is equal to Q over 4 pi epsilon naught R, excuse me, and this was R squared. So from that, what you can realize is that the voltage at breakdown, VBD, is actually equal to the R times the electric field at the breakdown. Now, what that means is if that radius is really, really small, then you can actually have a breakdown voltage that's quite small. In other words, way less than millions of volts. And that's the significance of a lightning rod. So lightning rods, which somewhat was invented by Ben Franklin, basically he discovered that a low radius circle tended to attract charge disparities in voltage would build up on it. And therefore he put little pointy objects up on top of a house. Those little pointy objects would act like chum in the water for sharks, but it was actually chum for lightning bolts. And the lightning would fire from the cloud, hit the actual lightning rod, which then had a very robust connector or conductor running from the lightning rod straight to ground. And by doing that, you would actually cause the actual clouds to discharge before the voltage got really, really high, because every time a cloud would float over your house, that pointy little lightning rod would compel the actual cloud to send a streak of lightning down through it, or even just to disperse lightning through it in a very minor lightning strike, which would reduce the voltage of the cloud and therefore make it less likely. Now, you are literally making your house a magnet for lightning bolts, but it should happen so rapidly that you never get a huge lightning bolt. And even if you did, it's going to go straight to ground unless some goober bought your house or you bought your house and decided to remove those weird looking iron rods that ran from the roof and the lightning rods down to the ground, which I have seen happen before. So don't do that. All right. So anyways, that is sort of partly why lightning rods work. So I'll write this down here so you can refer to it later. And if you notice, if you walk, for instance, on our Chesapeake or on our Virginia Beach campus, or the new buildings on the Chesapeake campus, you'll see that they have several little spikes sticking off the top of them. It's harder to see the actual wires that run to ground, but those are, in fact, lightning rods meant to prevent very bad lightning from happening. Anybody have any questions? Your book says, caution, breakdown voltage is smaller at sharp points because V is proportional to R0. So that's what I was talking about. In fact, if you actually have a lightning rod like that and there's a bad storm going around, you can look up and you'll see a little glow right around that point. That's actually called St. Elmo's fire. And we used to see them on the masts of ships. And of course, for some reason, they decided to make that into a 1980s era movie with Judd Nelson and the basically the modern version of the Rat Pack, which was nothing even remotely cool like the Rat Pack was. But anyways, that's the films like Pretty in Pink and all that stuff. But St. Elmo's Fire, of course, was one of them. Anybody have any questions on that? All right, now that we've done that, we've gotten all these neat little charges, all these neat little formulas. So I'll remind you again that the electric field is equal to E, the electric field due to a charge Q at point P is equal to Q over 4 pi epsilon naught. And I'm going to write magnitude RP minus RQ. And I'm going to cube that instead of square it because I'm going to put RP minus RQ down here. And that's a whole vector quantity. So that made the magnitude go off by a factor of R. So if I add a R at the bottom, that will cancel that out. So that's actually the electric field due to a point charge. And we're wanting to know the specifically at P due to Q at RQ. So we're imagining a vector that points from the origin to the center of charge Q, and we call that vector RQ. And then we imagine another vector that points from the origin to the point P at which we wish to know the electric field. And the electric field in vector form is, in fact, all of this mess. And what I'm telling you now is we can also say that the voltage at P is going to be equal to Q over 4 pi epsilon naught times, this time it'll be the magnitude of RP minus RQ. And this time it's just going to be a single power because I don't need a vector on top to give me a direction because V is a scalar quantity. And I realized that the voltage is only inversely proportional to R as opposed to inversely proportional to the square of R. Now, if I wish to compute the voltage due to a charge distribution, then I could say dV is equal to dQ over 4 pi epsilon naught RP minus RQ. But to be honest with you, there's really no need to go through all that nasty vectorness even to find the magnitude. So I'll just tell you that that's in general the formula that we can use, just like we did with Coulomb's law. And of course, we always use dQ. Actually, let me rewrite that in a neater way. dQ has got to be equal to lambda times dL, or it's got to be equal to sigma times dA, or it's got to be equal to rho times dV. And if it's uniformly distributed, then the lambda or the sigma or the rho is a constant. Otherwise, the lambda or the rho or the sigma can be actual functions. Anybody have any questions on that? Okay, well, I'm going to stop it at that point. We actually have about 5 minutes left, but there's not really much I can do. I guess I could do this. Let me do this real quick example. I'm going to say what minimum, there's my alarm, what minimum work is required to bring a charge 3.00 microcoulombs from a great distance away to a point 0.300 meters from a charge of 50.0 microcoulombs. So what we know is work is equal to Q times delta V, which means work is equal to Q times VB minus VA. And what we're going to imagine is that VA equals 0 because RA is essentially infinity. So that's one way we can think about it. Therefore, I can calculate that the work done would be equal to the charge, which is 3.00 times 10 to the negative 6 coulombs, times, now I've got to actually calculate the voltage at the distance of 0.300 meters. So that voltage is going to be, since it's caused by a 50 microcoulomb charge, it's going to be 50.0 times 10 to the negative 6 coulombs divided by 4 times pi times 8.85 times 10 to the negative 12th coulombs per voltmeter. And then that distance that we want to bring it away is going to be the 0.300 meters, like that. And then I'm also, of course, going to bring it from the 50.0 times 10 to the negative 6. But in this case, actually, let me write it a little more clearly. I'm going to say I have to take the limit as RB, or excuse me, as RA, approaches infinity, of 50.0 times 10 to the negative 6 coulombs over 4 pi epsilon naught times RA. And you can see that basically this quantity is going to 0, so that now I can calculate that the answer is 3e to the negative 6 times 50e to the negative 6 divided by parentheses 4 times 3.14159 times 0.300 close parentheses, and this gives me 3.979 times 10 to the negative 11th. Now, in this case, notice one of the coulombs cancels out. I get a volt times a coulomb, which is a joule, and the meter cancels out. Yeah, so this is actually 3.79 times 10 to the negative 11th joules. Ooh, I forgot something. I forgot the 8.85. So let me clarify that. Hold on, everybody. I just forgot to do the 8.85. So now I'm going to do 3e to the negative 6 times 50 e to the negative 6 divided by parentheses 4 times 3.14159 times 8.85 e to the negative 12 times 0.3 close parentheses. This time it gives me 4.496. Darn it. And that's 4.496 joules. Okay. So that is very much like example 23.6. And we're done for the day. It's exactly 7:50. I finished on time. Yay. So everybody, I'll wait around till the last person leaves in case anybody has any questions, but you guys are free to go. Do make sure you knock out your homework 22 before the weekend. Though it isn't going to be due tomorrow, I'm definitely moving it back a little bit, but you're not going to have till Sunday to get it done. So make sure you get it done before then. Have a good one. Thanks for coming, everybody. John, did you have a question, sir? Don't think he's here. Nope. All right. See you, everybody. Bye-bye.